Hi, everyone. And today I'm pleased to discuss one of the brand new AI projects, which is called AppAgent. So imagine you have a smartphone and you have various apps and you want to do some tasks on them autonomously, like, for example, navigate Google Maps, go through some Twitter feeds, type maybe your WhatsApp messages and so on. So this is something that may be too good to be true, but it turns out that using GPT-4 vision, you are able to do quite a lot of tasks reliably just through some clever inputs of the screenshot as well as where all the various interactable UI elements are. So I'll just go through this introductory video by this team at Tencent. And then after that, we'll go into further discussion about how this works. So here's the video.
Welcome to an exciting journey into the world of AppAgent, the next generation mobile assistant. This innovative technology is not just another app, it's an intelligent agent powered by large language models, designed to effortlessly navigate and operate a wide range of applications. Imagine an agent that not only understands app interfaces but interacts with them through human-like gestures such as tapping and swiping. AppAgent transforms our smartphone interaction experience, making tasks like finding the best routes and restaurant recommendations on Google Maps as simple as a conversation. AppAgent's capabilities extend to managing your communications. It can assist you in composing and sending emails, making staying connected simpler than ever. Furthermore, AppAgent demonstrates its versatility and creativity in complex tasks like image editing. It intuitively understands your editing needs, applying sophisticated adjustments to photos with precision and flair, much like a professional editor. That's cool. Now, let's delve into how AppAgent operates. It starts with an autonomous exploration phase. By observing changes in graphical user interfaces of various apps, AppAgent learns their functionality and operational logic. This deep understanding of GUI elements is crucial for its intelligent interaction with apps. With sufficient observation, AppAgent becomes adept at using an app. This knowledge is meticulously compiled into a document. Once this learning phase is complete, the agent is ready for action. AppAgent is equipped to handle high-level tasks across any supported application. Upon encountering a new user interface, AppAgent refers to its knowledge base in the document to understand the interface's purpose and usage. It then strategizes the best way to accomplish the given task, making the correct operation step by step. This methodical approach enables AppAgent to efficiently complete a variety of complex tasks across different applications. Isn't this fascinating? Visit our homepage to try out AppAgent and witness its capabilities firsthand.
All right. Actually, that was a pretty good marketing video, if you ask me. So now that we have seen the capabilities of what AppAgent can do, let's go into more of the technical details. So, of course, I do not intend to just go on the surface like what that video did. We will delve more into like how the code is done, what are the prompts, and I'll give some of the what I think could be improved. Okay, it's quite good already, but it cannot do everything. So let's see why. All right. So AppAgent, what's the motivation behind AppAgent? So before I continue, can I just check, are the slides visible? So you should see the motivation slides right now.
Yes.
Okay, thank you. So for AppAgent, the main intuition or the main motivation is that we want the AI to be able to operate the apps, okay, not at the system level meaning like code level. So if you are using some like Python code, maybe you write Python functions to execute it. No, we don't want that. What we want we want the AI to be able to access the GUI, graphical user interface, just like a human. So you can tap the UI element, you can swipe, you can enter text via the keyboard and so on. So all this is the key consideration so that it can be used across apps. Okay, it is much better to generalize if you do it at the GUI level than at the application level, because different applications might be coded differently with different backends. Also, another motivation that the authors have written in the paper is that this kind of AppAgent would be much more secure. Okay, because if you were to do it at the back-end level, sometimes you might, do some prompt injection, you might affect the database and so on. But if you do it at the GUI level, okay, you are just limited to what the user can interact with. And it's actually much more secure because apps usually are designed such that the user does not break the system. All right. So you try WhatsApp or X, you can't really break their database just by tapping or interacting the UI elements. So that's a plus point. So how can we get the AI agent to do it? All right, so before I go into the specifics, I'll just want to recap on React. Okay, the reasoning and acting framework. Who here has heard of React? Raise your hand. Anyone has heard of React? Okay, some of y'all should have heard. Okay, so the rest, have you heard of React? Okay, so, all right, Philip has heard of it. Yeah, so if you haven't heard of React, now's the time to hear it because you'll be hearing it from me many, many times, especially in the next few videos where I'm covering about agents and so on. This React framework is known as the reasoning and acting framework and has been proven quite successful over multiple agentic implementations. So what exactly is React? So the first thing to note is that traditionally yeah, Philip, you raise your hand. Okay, I'm sorry. Traditionally, the LLM is enclosed. Okay, it's in a world of its own. It doesn't know how the environment is. So we need to sort of give it the environment observations into the large language model. If not, it exists in a black box. So React does just that. It gives the observations from the environment into the large language model. Okay, so if we just do it like that, this will be like, say, Ken, the robot, kitchen robot that picks a can of Coke and so on. You just give the environment observations and ask the language model to pick an action. Okay, but that's not enough because as you know, LLMs may not do action planning very well, especially for long horizon tasks. So how do we give it the planning edge? That's when you put in this reasoning part. Okay, reasoning part is basically like, what's your thoughts? Okay, this is like a chain of thought. You can even use it to do like tree of thought or more of the advanced methods to do reasoning. But the idea is you put in some form of reasoning here. So you can do chain of thought. You can do like tree of thought, for example. Yeah, so there are various ways to do this. But the idea is you can ask the large language model to do some thoughts over here to help it to plan for longer horizons. And the observation comes from the environment, okay, which ground the LM to the environment. So with these two, thoughts and observations, all right, then you can choose your action. And the action over here, typically we will give some form of functions so that the agent can just pick one of the functions. Okay, in general, it's good to constrain your LLM agent's outputs. Okay, because if you ask it to generate things without bound, you may not get what you intend most of the time. So it is good if you can ground it in some functions. So this thought action observation, or otherwise known as the React framework, is very popular. It's used in a lot of architectures such as LangChain. All right. So you can use this for many different tasks, and I've used this before as well in my own agentic implementations. It works quite well. So this is the framework for the paper as well. They did not change this architecture. It is largely similar. How do we do this for images? That's the question, right? Because this we can do it for text. How can we do this for images? So you can apply the React framework, okay, in the input phase from the environment, okay? Because you see over here the observation. The observation here, the observation is typically a text. But how do we make this observation into like to cater for images as well? And the answer is you can feed in an image. All right, and when you feed in an image as image tokens, the GPT-4V can use this to do reason over text and image tokens to get observation, thoughts, and actions. Okay, so you realize there's something here that is different from the previous slide. Okay, in the previous slide of the React framework, you realize that they actually did thought, action, observation, right? That's because at the beginning here, we already give the like observation of the previous step. So over here, they use observation, thoughts, action. Actually, it's the same thing. It's just a matter of like how you define the start of your step, all right? So given the image tokens, okay, and also given a prompt, like for example, over here, I want to say like, I want to complete the task, which is like maybe this task is to type to Agent Liu, all right? So your prompt is, I want to complete the task. I want to type to Agent Liu this message. Okay, then you give it the image tokens, which is this screenshot itself. Okay, then you ask the large language model to say, hey, give me the observation of this, like, so over here, you can see that the agent says, oh, the observation is that the screenshot shows the Telegram app, from Agent Liu. And to complete the task, I should go and type the answer to the text 7, which is I think here. All right, if I see correctly, it's over there. Yep. And then after that, you should type in this text here as your action. So you can see this, basically everything is the same as React. The difference is that the input part from the environment, okay, it's both, okay, the prompt itself and the image of the screenshot here. Okay, the prompt is basically saying that, hey, these are the functions, and choose the right function based on this input. So the environment will give you an image, which you will then process using a certain prompt, and then you perform the React framework accordingly. And this kind of works across different applications as well. Like you can see, it works across this Lightroom is like Photoshop, Flock, and so on. Okay, any questions so far regarding React? Okay, so this is the basics. Now let's see how we process the image modality, because image modality is something new, right? Traditionally, in many of the large language model systems, it's been text only. And now with text and image models, it changes the game altogether. You can now interpret images. Let's see how they do it. Okay, so before we go into the image component, I'm just going to give you a broad overview of how AppAgent works. So firstly, we have the screenshot. Okay, we also have all the UI positions from XML. Okay, and then we go into the exploration phase, where basically the agent, it will just do like actions to try to get to the goal. Okay, it's not random actions. Okay, let me highlight, these are not random actions, but goal-directed actions or task-directed actions, or it can be human demonstration. All right, so this helps the agent to learn, okay, based on like some of the pre-built stuff in GPT-4. Okay, how do we get to the goal? And it turns out GPT-4 is actually quite good at getting to the goal. Okay, I tried it out. Even without images, it can get you the right steps most of the time. All right, so this exploration phase is really just using GPT-4's ability to get to the goal. And then the main thing over here, okay, and I think this is a very, very nice thing, is memory. Okay, memory in the form of functionalities. Okay, we learn the functions of the UI elements through exploration. Okay, the text can't be seen, but let me just put it here. So this, I like it a lot, okay, because I love memory, and this is really learning by memory. Okay, as we explore, we compare the start and the end state. So for example, if you look over here, you tap and then a UI appears. So from this, okay, this is actually like Thousand Brains theory, where you learn from an action and then you observe what changed after you made an action. So after we do a tap on this Lightroom app, all right, a menu appears. So then we can conclude, okay, the human can look at the two of them and then look at the difference and conclude, okay, tapping this allows me to open some settings. All right, it's a very logical conclusion, very natural conclusion. Actually, I have a 3-year-old kid. All right, he likes to play my phone. So I realized something. All right, I never really told him how the phone works. But after he tap, and then he managed to find my wife's photo and then do the video call and so on, he's able to do it by himself. Okay, even though I didn't really say, hey, this button does this. Okay, he might have observed how I do it once and then he just replicated it. But sometimes he also learns on his own. He just plays around with the phone and then, oh, when this very nice UI interface appears, he tries to replicate again. And it turns out that he can do it quite well. All right, so it turns out that the secret to learning is just observing how our actions impact the world. All right, this is a very crucial point. Let that sink in a bit. The secret to learning is observing how our actions impact the world. Okay, this I think will be the key to all the breakthroughs in the next few years. Right, action-led learning. Okay, because if you don't take any action, you can't really learn much. I mean, you can watch videos and so on, but you don't know how to interact with the world. Like if I'm a human right now, I can move forward, I can move backwards. But if I don't know what action I'm taking, I don't know what my action impacts the world with. And essentially, I don't know how to plan with the action next time. Like, for example, the action drink water, you see, like this. I need to execute the action and observe what changes, like my body state becomes more hydrated and so on. If I don't have the before and after state of my action, and then I cannot learn from what the action does, essentially, I can't really learn much. So I like this a lot. Okay, this before and after, and then use this action and then try to learn what this action does. Okay, there's one caveat here, all right? In the real world, what your action does is dependent on the state of the world you are in right now. Okay, but for this app, because the UI element always does almost the same thing. So this kind of means that like it's more constrained. Like in the real world, what your action does is actually more context dependent. So over here it's like what your action affects is usually context dependent. Okay, but in the documentation, they actually don't really have the context. They just say that, okay, this button, okay, helps to open the color settings. All right, so there's a slight constraint here, because if this UI element is used with different functionalities, okay, you can imagine a game, all right? Maybe you have a tower defense game. You have this deploy button to deploy the tower. But every time you press the deploy button, it depends on which tower is selected. So this limits the effectiveness of AppAgent, because as far as I know, their documentation is not context dependent. It is just UI element dependent. All right, and that is what is missing. Okay, so this is something that I think can be improved. All right, but this idea of action-based learning, great idea. All right, so how do we do the deployment then? The deployment is like that. So after you have learned how the documentation is, okay, we then feed in the documentation, okay, and then we ask the agent to do in the React framework. Give it the task, okay, give it the current image, give it the documentation of how the UI elements work, and then, give it the list of functions to do, like for example, tab. I mean, I'll just write it here. Later I'll go in detail. Tab, text, tab in the text, swipe, and so on. So you ask it to choose the action. So it chooses the action. Maybe the first action is called tab element number 5 or something. Yeah. So you do step by step until when it reaches the end, it will give like an exit, which means that it has done the task. So essentially, 2 phases. First phase is to explore, find out what each UI element does. That's the exploration phase. Second phase is to deploy it and basically do the functions needed one at a time until you reach the end state. Okay, so that's a broad overview of how it works. There's one last thing here. Over here, you can see that there's observe, think, act. This is the React framework. There's a summarize. Okay, what is summarize? Okay, summarize is basically like this. You want to summarize all your past actions, so that, when we give it as context, we also give the past actions. Okay, you have clicked on this UI element before, you have swiped up before, and you have reached this state. So you summarize your past actions, okay, and give it as input to the agent. So the agent knows that, okay, you have swipe up before, maybe you shouldn't swipe down because you go back to the previous state. You continue from there. So why summarize the actions? Okay, because if you don't summarize the action, sometimes the agent might be like confused. Like if you go up and go down, actually stationary, right? So your summary of the past actions can be I remain stationary. So it helps to consolidate the past history better. It's something like if you are in a chat conversation, right? So if you have a chat bot, you summarize the conversation history. Okay, so that the agent is able to better use this to make decisions. So it's the same logic. So that's the key extra thing apart from React. Okay, so I more or less covered everything that I'm going to cover today in a very brief manner. Any questions so far? Okay, maybe I just pause here for 1 minute in case you all have anything you want to ask, like the broad overview. Okay, Kai, you asked, does this method work for desktop application too, like drawing a flowchart in Microsoft PowerPoint? I would say yes. Okay, as long as you have a way to identify your UI elements, then you would be able to give the UI elements numbers here, like the 1, 2, 3, 4, 5. You can give it the number and basically ask the app agent to click on the right elements. Okay, the reason why this is a smartphone app right now is because they use XML, all right, the XML code from the smartphone to basically identify where are all the X and Y coordinates of your elements. Okay, they basically go through the XML code, find out what is interactable, and then you can find out where are all the bounding boxes for the UI elements. So for Microsoft PowerPoint, I'm not too sure whether we have an equivalent where we can already identify the where the buttons are. Okay, but if we do, then we could use this to work for Microsoft PowerPoint as well, or other kind of applications. Okay.
Oh,
yes.
sorry. One thing based on what Kai said. So I mean, selecting the buttons and moving sliders is one thing, but actually drawing in like an unconstrained space on Microsoft PowerPoint might be a whole nother feat. Wouldn't you agree, or do you think it's actually capable of like drawing things and charting out things?
Of course, I mean, the whole idea of writing things out in freehand, like for example, if you want to draw like number 2, the strokes and everything, that's a huge domain, right? This is a huge action space. And it's something that is not easy to be done with just like button swipes or button clicks and text. So that unlocks an entirely new thing. So like, for example, you could have a DSL, a domain-specific language called draw. And then over here, you can like convert maybe text to strokes. Yeah, you might need some form of abstracted functions in order to still do this kind of method. Because if you were to do each stroke individually, there's just too many actions to do. So I think it's still possible to use this kind of framework, but you need to do multiple layers of hierarchy, whereby you abstract away things into functions. Then you can possibly use this. That does it make sense?
Yeah, makes sense. So the underlying logic seems like it's a picture recognition sequence. Like it can recognize like what position you're moving through a series of pictures, right? Is
Yeah.
that the underlying logic?
Okay, so I will go through the logic later. There's a few slides on this, so I'll answer that question later. Joni, you asked how are the XML positions generated, right? Was it learned? The answer is no, it wasn't learned. It's totally rule-based. If you look at their code on their GitHub, they basically look through the XML elements, find out which are interactable, and find out the bounding box positions of each of them. Okay, so I think this is a good segue to go to the next part. So if you have any more questions, we can ask through the presentation, no worries. But I'm just going to go through how this multimodal processing is done, okay? Because a lot of people have asked me this. I think this is a key thing. Okay, before I move on, I just want to say that GPT-4V is quite good at intent processing, okay? But it is not good at UI navigating. So I would say the key contribution of this paper will be how to give good UI navigating skills to GPT-4V, all right? So we will cover some of the key concepts before we go to the 2 phases, the exploration and the deployment. The first key concept is like, how do we do the multimodal query? All right. The second is how we process these UI elements, okay, which is what Joni asked, all right? And next, we also go through a bit of what is the domain-specific language they created in order for the app agent to be more performant. How do we limit the scope of actions? Okay. So some brief primers, all right? If we ask the UI elements to be generated by GPT-4V, I tried. Okay, it doesn't give very good positions. All right, that's why XML was used. All right, and not just the XML bounding boxes. They also give it the overlay of the numbers on the screenshot itself. So as an input view, we have the XML with all the UI elements, positions, and everything. And then we also put the corresponding numbers in the XML on the screenshot so that GPT can correlate. All right. Then for the action space, okay, you can see that they also have the XML part to ground where the different elements are. So it's both XML XY positions as well as the image overlay. Let's take a look at how this is done. So first up, I'll introduce how GPT-4V works, okay? For those who have not used the API, it is actually about the same as how you would do a text-based stuff. It's just that now, because we have images, you need to define your type over here, and then you can put your text prompt here. And if let's say if it's a URL, okay, then you define your URL over here. So essentially, this is the way to do multimodal query with the GPT-4V API. You just pass this content into the check completion API. And in this content, you can have both text-based as well as image-based kind of inputs. So this is quite revolutionary because instead of just giving text as a context, you can give it another form of abstraction space, which is the image itself. And you can query the image. You can say that, like based on this image, what should I do next? All right. You can query action to do, and then the resulted action can then be fed into the Android emulator or your Android phone to carry out the action. So let's take a look at how this is done. Okay. This other query, all right, is for if you want to generate your documentation or you want to do some reflection of your actions. Instead of just having the text-based prompt and one image, you can have two images. So this is the before image, and this is the after image. So what does this do? So this is the before image, and this is the after image. Given both images, you can ask it to reflect, okay, to find out what is the UI. You can ask it to generate documentation. Okay, you can also ask it to reflect on its actions to see which action is good. So how do they do this? I'll cover this in the deployment in the exploration phase later. But the idea is you can see that GPT-4V is quite versatile. You don't have to exactly just give it one text and one image. You can give it multiple text and multiple images. You just need to add in more things into this content list. Right? Go try it out. It's quite cool. Just that it takes about 3 cents per image. So be careful with your spending here. Yep. So this is how GPT-4V works. And let's see how this is done using one of the examples that they have. So over here, they have this example on their GitHub where basically they are using Google Maps and the task is to find out where is Tencent Shanghai branch. So you can see that over here, what we have is that we have different numbers overlaid here, right? These numbers here are actually the XML files, XML UIDs overlaid on the screenshot. Okay, and there will be an XML given to the GPT as well, which will tell the GPT where exactly are these elements. Okay, so I'm not too sure whether the XML file actually has the description of elements. Okay, this one I'm not sure because I haven't really looked into the XML file. But if it has the description, then that's even better. Okay, because then the description, okay, because I think the description is a plus if there is, might tell us the functionality. All right. So basically there's two views. One is this screenshot with the element overlaid, all right? And then we have this XML file with all the element positions. Okay, description, I don't know, but if there's description, even better. Okay, so these two views, quite powerful, okay? Because if you don't give it this UID view, okay, and you just try to ask GPT, I want to type in Tencent Shanghai branch, what do I do, right? Honestly, you ask GPT to navigate to the right X and Y position of your image, I think you will fail most of the time. In fact, they actually did that, and then you will see the results later. 2% success rate compared to 40% plus if you use the this UID elements and everything. Yeah, so this is a huge drawback of GPT-4V. It doesn't do exact positions very well. You can go and try it out. I tried it out on the abstraction and reasoning corpus. It doesn't tell me the right grid size sometimes. It doesn't tell me the right configurations of shapes and everything. It's not very good at precise pixel kind of observations, but it is quite good at general image observations. So that's why there's two views. I always say that like for smart agents, we should have multiple abstraction spaces. These are the two abstraction spaces. One is an image abstraction space. One is like maybe a position abstraction space. Maybe if you view in your in your brain, it might be the vision module, and then maybe the grid cells, place cells module. Or maybe even the vision module might be like vision space specific module. So where you can actually tell like roughly where it is, but you need to anchor it somewhere in the world. So there could be different modules and then you join them together to make a decision. And this is somewhat like that. All right. So Philip asks, what if you lay a grid over the image like a map might have rows and columns? So indeed, that is what they have recently added in January. They did a grid view. So I'm not going to cover grid view today, but the grid view is basically you split your screen into multiple squares like that, and then you number each square with with a number, and then you overlay this grid and pass it to GPT. So this is like cell number 1, cell number 2, cell number 3. Okay, why did they do this? Because if you use XML, right? Sometimes, you know, your XML tells you that, okay, maybe Google Maps, this entire screen can be scrollable, right? Right, but to the AI agent, is like so freeform. You can scroll this way, that way, or swipe. There's so many things you can do. Sometimes, like, you want to go to this precise position of the maps and tap it, but you're unable to do it because your UI element spans the whole screen. All right. So for stuff like this, grid view might help because you can go to the kind of position here, but it doesn't help completely because let's say if I want to tap on this green color thing, let's say this green color thing is where I want to center on, you know, the spatial resolution of your grid view may not be enough to go there. You might need a smaller grid and so on. So grid view will not solve everything, but it can help you to tap places whereby it's not defined by the XML elements, right? So that is indeed a limitation of AppAgent. Okay, and I think this limitation is something that with just their domain-specific language, you are not able to do this yet, all right? So how do you assign the number or LLM assign? Kai, you asked this question, right? Do you assign the number or the LLM assign? You mean the
Yes, right.
UI element numbers, is it?
Yes. Like the 15, right? 9,
Yeah.
10. Like how did you
So
get those numbers?
these are not by LLM. These are all entirely rule-based. When you pass through the XML code, you can number each element one by one. So like the first element you see is element 1, element 2, based on just the XML code itself. So like as long as the element has a property called interactable, like for example, this search bar is interactable, then you can label this search bar as, okay, this is this, or like this one is interactable. So this number 1, this is another interactable button, and so on. So all these are labeled using rule-based. You just pass through the entire XML, find out what elements can be interacted with, and then you give it a number.
So it's
Yeah.
a user, so it's a user and programmer assigned number, right?
Correct. So you can treat it as like you have God's view, all right? So the XML is like God's view. You know exactly when you create this app, these are all the buttons, all right? These are all the positions of the buttons. And then what I do is I just, based on the order of my first scene, I just label each button as a number. So all these are done through code, and it's fully deterministic. There's no LLM involved at all.
Oh, got you. Okay, thank you.
Yeah. But you can see based on this Google Maps, you can see the limitations already, right? It has a lot of numbers, but then how do you swipe the entire screen of that Google Maps? A bit hard. Yeah. So you can't really do that. So this is another thing to take note of. You are limited by two things. By the input views, or rather the agent is limited by the input views, because if your input view doesn't have that small resolution, you can't do it. GPT-4V is not good for small resolution stuff. Trust me on that. You can try it out. It doesn't work very well for things that require precise navigation. And the other thing is your functions, or your DSL, your output action space functions. So if you don't have that particular function, like over here, they don't have this thing called zoom in, zoom out, because that's not in the DSL. So you can't really do stuff like zoom inside the Google Maps for AppAgent. Okay, so if you don't have the action space, you can't do it. Just like, for example, humans, we can't fly, right? So you don't have the action space to fly, you can't do anything that requires you to fly or flap your wings and so on. But we do have action spaces like walk, run, and so on. So ultimately, what your agent can do is dependent on what it sees and what it's able to do. So these two things. Of course, there's also other things like processing ability and so on. But let's just assume that perfect. Okay, that you can do the reasoning perfectly. But the main thing I like to highlight is that any agent that you create will ultimately be affected by your inputs and your outputs. So how performant it is depends on how well these inputs and outputs are suited to your task at hand. So I would say that for AppAgent, it does most of the tasks that it selects quite well, because most of the tasks are just tap and type in text kind of stuff, or scroll the UI bar, which is possible because all these are observable to the agents. They can see the scroll bars and everything. So that's good. And just want to add, the AppAgent, they will also overlay this huge finger here so that the agent knows where's the cursor. All right. So this is just to make sure that GPT-4V knows the cursor is there. Right. In the XML elements itself, they will also put where the cursor position is. Okay, any questions so far on this XML and image overlay? I think this is one of the most important for this paper because honestly, I haven't seen anything like this before. This is an attempt to make GPT-4V understand UI elements. I would say it's a good first attempt. It's not perfect, of course, but at least it enables you to have a very, very minimalistic DSL, domain-specific language, to limit your action space. So I like this a lot. Okay, so it looks like everyone's okay with this. So as you can see, after we fit in the image here, we ask for the observation, then we ask for the thoughts, and then we ask for the action. So you can see over here, the action is tap 15, which is tap this search bar. So this is them, all right? I actually did some experiments myself. Let's see what the result is. I basically just do a screenshot of whatever they have here. And then I ask in a very simplified way, all right, how do I search for this? This is the task. All right, then I tell them the element UID numbers are overlaid on the picture. Answer in the observation thought action format. And then I give a very, very simplified action space. I didn't even describe the action. Okay, I just say tap with the element UID and text UID and the text. Okay, in the DSL template, their text is just like text alone. Okay, it doesn't have this element UID. Okay, which I think is a waste because like I think it'll be nicer if you could just do the text directly on the UID. Maybe that would solve some problems because this is essentially a two-step process. I mean, if you want to key in text, you have to go to the element UID anyway, right? Yeah. So I just thought that maybe they could have improved their DSL by just including this. Okay, but anyway, the thing that you can see is that the text part for the GPT-4V will be what I type in here. Here I just did in the browser interface, but if you do it in the API, it's the same thing. This text here will be going to the text, and this image will be this image here. So if you want to do before and after, you just need to have another image so that you can do the before and after comparison. So how does GPT do, right? In my own app, this is a very, very simplified prompt. Their prompts are too lengthy. I don't like it. Okay, so if I were to redo this project for them, I think I can improve their performance. Okay, their prompt engineering is not very good for this AppAgent. All right, so this is the like I think more concise and shorter prompts generally help the LLMs perform better because they don't do well for long context. So AppAgent could improve on that. So let's see how this works. All right, how good it is. So ChatGPT does this. They gave me the observation map application. Yes, good. Okay, thought to search for Shanghai branch, I will need to use the search bar at the top of the screen. Very good. It knows how to do it. All right. We need to tap on the search bar and then enter the desired text. Awesome. Perfect. GPT-4V, full marks. Okay, it answered everything correctly. Okay, let's see whether the action space is correct. Oh, tap 1. Tap 1. One is actually this thing here. Yeah. So over here, they say tap 1, select the search bar. Unfortunately, this is number 15. Okay, so if let's say there's some sad music here, this is the place where the sad music will come in. All right, it got full marks under here. Great work, GPT-4V. Then the action space it used the wrong UID. All right, so what does this tell me? All right, it tells me that if we just give in this image view, all right, with the overlay of the numbers like that, GPT-4V is not able to get the UID numbers correct all of the time. All right, there will be a source of failure here. All right, that's also why the XML is needed. If we don't put in the XML here, all right, it might get the wrong thing. So let's see what happens if we put in the XML. All right. So okay, I'll skip this first. Let's see what happens if we put in the XML. All right, let's suppose that the XML says that, oh, this is the search bar, this is the explore button. Of course, I don't know whether there's a description there, but I would suppose that XML usually will have some description. So if not the description, it will at least give the X and Y coordinates so that GPT can do some reasoning where say, I want to go to the search bar at the top. Then from the XML, you can tell which are the elements at the top. Okay, let's suppose we can do that. I run the same prompt again with, let's say this is the XML. Okay, this is to simulate the XML. Okay, because the real XML is very long. Okay, I don't really want to do that. We just simulate it, and you can see that, woohoo, it got it right now. Look at that. Perfect. Okay, it has achieved full marks in this simulation. All right, so what have we learned here? Okay, or what have I learned here? you need to provide the description of the overlay UID, which is this XML stuff. If you don't give the XML stuff, its general intent is okay. But when it comes to UI, it doesn't do the UI that great because it doesn't know where to click. Okay, so the XML is like a bridge the gap thing where we give it enough resolution such that it now knows what to click on and it can relate to the picture, right? So we have just shown, okay, from this very simple example that just this picture alone is not enough. You need the XML, all right? If not, or you need a way to, if you don't do XML, you need a way to like decompose the images. So someone in my Discord was telling me, Crit was telling me that, why not use segment anything by Meta, right? Okay, I'm not very sure whether segment anything can get you all the UI. Okay, because UI sometimes is not that obvious. But that could be a possible way instead of using XML. All right. There could be other ways, like people would have some UI specific models, okay, that you can decipher the UI without XML. Sure, you can use all this, but the idea is you need to augment GPT with finer grained resolutions, because GPT-4V is not good for at this. So this is the idea of multiple abstraction spaces. One abstraction space may not be enough to solve a problem. You might need multiple abstraction spaces together, jointly, they can solve the problem. Okay, so I actually did another experiment that was quite interesting. So I just want to share. Okay, so this is basically, I just want it to describe the image. Okay, I just give it the screenshot. I asked GPT-4V to say how this image is. Then it gives me, oh, this is Google Maps. Great. So actually screenshots, GPT-4V has training set on it. Okay, it does it quite well. It even knows that, oh, there's Chinese character, English character, there's restaurants, hotels, shopping. All right, not bad. It got all this correct. So in terms of basic UI processing, it's able to tell like roughly what this is, like explore, go, save. Okay, so it's able to tell all this. So GPT-4V has this capability. Okay, just not very good at positions. Okay, so you can see we will click at the search bar at the top, all right, and then you should type in and then this one. So the key challenge of AppAgent now, okay, is not the GPT's understanding. The key challenge is how do we get GPT to know where the UI elements are precisely? And that is the challenge that AppAgent tries to solve with the XML overlay. Okay, let's go on. I think I have one more thing that I did. Yes, as a slight aside, I wanted to see whether, is the image really necessary? Can we just do only the text? All right, so I did the same experiment. I basically just type in this one. Okay, sorry, not this one. I basically type in this. I type in this without the image itself. Like, how do I search for Tencent Shanghai branch on Google Maps? So I just translated the app into a text, all right? And then I say that, oh, we have these elements, UID, search bar, explore button. And you can see that in general, it got the actions more or less correct. Okay, just that, instead of tap first, then text, it did the text, then the tap. All right, so without the, and also it's because maybe my DSL is given like that, all right? So without the images, your DSL understanding might be impaired, but you can make it up with more description of the functions. Okay, because like it's something like I ask you to do some like I ask you to do some actions in a world you have never seen. All right, so you also play like maybe a video game blind, like up, down, left, right. You don't even know what's going on there. But I give you inputs, okay, like you're playing Super Mario. Oh, your character jumped up. Oh, there's a mushroom in front of you. So you have to interpret the world like using text only. So if you don't have the image stream, you might need to give more description because you need to compensate for what you miss out from your images. So text only interface will likely still work for AppAgent. You just need to be more verbose in terms of how you describe the image. Okay. And actually this method, might even be better than just using GPT-4V directly, because GPT-4V may not be able to distinguish the fine details yet. All right. But in general, I agree with having an image because an image would help to simplify the problems for quite a lot of stuff. Sometimes you cannot describe things well in text. The spatial information is best seen in an image. So GPT-4V, I believe they use vision transformers. Vision transformers have like XY encoding for the positions as well in the tokens. So they are able to get the kind of relative positions better as well compared to just using text only. So while text only interface can still work, the text and image will be a more powerful input space to work with. Okay, I see some chats. Let's take a look. So you ask, that might be hard if the model is trained with tokenized images. Okay, I don't quite understand this question. What do you mean that might be hard?
Hello, can you hear?
Yeah, I can hear you.
Yeah, so basically I'm saying for if you like, as far as I understand, transformer based model with vision capabilities, for those kind of model, the image or the visual modalities are trained with tokenized images, right?
Yes, I believe the images are trained using vision transformers, and the vision transformers are usually done like this. Like you take an image, like maybe a person here, you just split the image up into like, the famous paper is like an image is worth 16 by 16 words or something like that. Yeah, so they basically split the image into into boxes like that, and then each box they encode separately. I myself don't like vision transformers because I find that the way they encode this patch, you might lose the spatial interaction between patches.
Yeah, exactly. So that's my point. So apparently there are evidence suggests that trained with tokenized images, actually those models are not very good at spatial capabilities such as navigation or locate something. I think that's kind of corroborated by the thing you pointed out. So
Yeah, I mean,
unless I feel, yeah, so unless unless you I mean unless they have, you can come up with some different ways to train the vision modality of a multimodal model. So I think this will be a bottleneck.
yeah, I never liked the idea of VITs just tokenizing the whole patch like that. But recently I have changed my mind on some parts of VIT. I think maybe going by patches might be okay. Okay, why? Because actually the rods and cones in our eyes, right, in our cornea, they are also like sort of like working at patches. They have different resolutions. If you look at it, your vision is not this whole shit. Your vision is actually like little spheres of, or it may not be spheres, it's like different regions of awareness, and then you patch them up together. So there might be some good stuff about this patch, but you need more than one grid. Okay, I think a multi-resolution like kind of vision transformer might be okay. So like for example, you have another grid that does like this, like so you slice things differently. So it's something like you have a lens, then you shift the lens differently so that you can, like for example, if the head is here, sometimes your head is cut into two because of the squares. But if in a larger block, your head will be preserved. So I do think if you could have multi-resolution vision transformers and even stuff like I don't know, because right now our image processing might be done at different spatial resolutions, and even for the same spatial resolution, there might be multiple angles at looking at it. Yeah, you kind of need to replicate that. So more than one abstraction space. So I think if you can do this, maybe the output will be better for the image models.
Yeah, but anyway, so yeah, so my point is the current model doesn't do it
Yeah.
well.
That's why GPT-4V cannot do the. I asked it. I mean I didn't have the screenshot here, but I also asked GPT to say that, show me if this is 00 and this is like 150, what is the coordinates of this? It got it like very approximately wrong. All right. I mean it.
Yeah.
So let's say if I want to find out what is this, it gave me some region like that. Yeah. I mean, so it's not very precise, and I think the main reason is because like vision transformers, we're not really meant to train stuff to be very precise. Okay, if you look at it, human vision is not meant to be precise as well. Okay, like you tend to remember stuff very differently from their original aspect ratios. Like I give you a picture of maybe this Google Maps, I ask you to redraw again in your mind, right? Chances are you won't exactly recreate all this, right, at a specific locations.
No, but the thing is, for us, if you don't have a memory, we talk about we're looking right now, right? We don't see these segmentized, fragmented patches. despite I think I'm not sure it's the line of like
Yeah.
neuroscience research you mentioned, but that's really not what we perceive, right? Maybe
Actually,
there
that's
is
not
some
true. Yeah. We do perceive
post
things
process.
in a fragmented way. We just teach
No,
them
but
to.
if you zoom in, you focus on whatever part you want to focus on, you don't see discontinuity, right?
That's because the brain patches up stuff.
Okay, so you are saying, oh, maybe there's some like post-processing going on in our brain.
Yes,
So
yes.
maybe the model also needs we need to draw some parallel, and model also need to some similar technique to patch things up. But as it stands now, like it is still
Yeah.
it's still I think it's
Okay.
still a long way to go.
So let me share my view of how humans navigate the UI, all right? So as I said, we are kind of bad at spatial resolution as well. We don't really know the precise XY coordinates. If I ask you right now, okay, you look at me on the screen, what's the XY coordinate of me on the screen? Do we think in that way? Do we think in terms of XY coordinates? No, we don't think in XY coordinates. We are quite bad at that. That's why we don't interpret graphs very well, bar charts very well, and so on. We go by broad like overview, and then like if you really want to zoom into the details, then you need to pay attention and look at it. But by default, we don't go XY coordinates as well. The human mind doesn't work that way. Okay, but how come we can? This is a very interesting question. How do we navigate to the search bar so precisely, right? So I've been thinking about this question and I have my answer already. This is your initial cursor position, okay? Assume that this is your initial cursor position. Like GPT-4V, we are quite good at saying that, yes, there's a search bar at the top. So in your mind, okay, in your mind it's like that. In your mind it's like, go to search bar at the top. At approximate region 15. I mean, I think we might also classify the regions like that, but we don't have the XY coordinate. Okay, and the thing is, AppAgent might have the XML. Humans, we don't have the XML file at all. But how do we still navigate there? Okay, and this is where what I think happens. Okay, we know that, okay, this is my current position, this is my start state, and this is my goal state. So we already form a start state and goal state in our minds. Then the next thing is to move there. So we move, okay, but we don't exactly know for sure like our action will go how much, okay, but because it depends on the screen surface, whether there's friction or not. But roughly we know the general direction it is. So we slowly do the swiping, or slowly do the moving. And in some sense, sometimes we move wrongly. We move here. Okay, but because we know our end state is here, we correct ourselves and go back here. So essentially, it's a goal-directed movement. I mean, of course, in most cases, we don't swipe like that because in your mind, you already have some memory about if I take certain action, where will my end state be? Based on your past interactions with the world, you already have some form of idea of where your finger would go. So essentially, you are doing a step-by-step goal-directed movement of your finger, of your cursor, all the way to this point here. And to do that, you don't need to know the rough, you don't need to know the precise, location. Okay, all you need to do is just need to know where current position is and where end position is. Okay, in some sense, it's actually like my research, the learning fast and slow. You have your start state and your goal state, and then you want to go to your goal state, and then you use goal-directed action learning or goal-directed action selection. And in some sense, if their DSL was more of like, okay, move up, then they could do something like that where iteratively GPT would be able to say that, okay, my cursor is below my intended region. I need to go up. Yeah. So that's what humans do. Over here, they kind of bypass this step because this can be quite problematic. AppAgent just says that, hey, this is the search bar. You can just go directly here. So I bypass the movement step there, which I think works fine because, like, honestly, all you need to do for most cases is to just move to the UI element itself. Unless whatever Philip said, you want to draw a tool in Microsoft PowerPoint, right? Then you might need the strokes. Yeah. So those kind of use cases, you need to do like more precise manipulating of your cursor. But for most apps, you don't need this. Most apps just go to UI and interact with it. So I agree with what AppAgent is doing. It's just that we humans, we do things a little different. We don't like say, okay, go to that bar. Okay, go to this button and click. Okay, we actually have to move our finger there and press it. Yeah, so it's a bit different from how AppAgent does it. But I would say that why AppAgent gets it wrong, right? It's actually because when you want to interface this kind of very precise elements to like a very imprecise vision model, you will have errors. And AppAgent tries to mitigate this by giving the XML view, saying where the precise positions are, and also overlaying this so that you can map to the vision module. Okay. This might be a source of failure because like the mapping is not 100% correct. So the way to improve AppAgent is to improve the vision module. Or you have to make it such that like I don't really like this overlay actually, because like I find that it blocks certain information. Right? Although they say it's a translucent overlay, you see, it kind of blocks stuff like restaurants and so on. So I think the alternative, okay, is to, instead of giving it a view like this, all right, overlay view, okay, I was thinking of another alternative that AppAgent can do. You give it another view of XML elements alone. So you can just give it like this is 15. Yeah, so you can basically just like, instead of the original view, you can give it like an overlay grid of where all your positions are. So this is a separate image. So I think if you do something like that, the performance will improve because GPT is able to understand numbers if they are much bigger. These small numbers sometimes leads to errors. So yeah, this is another way to make the so I think the key way to improve AppAgent is to just make it such that GPT-4V understands the overlay part better for the UIDs. Because I think this is a key source of failure right now.
This is just, I'm thinking about like on websites and everything, like when you open up the, I can't remember what it's called, but the side panel there, and you scan over elements on the, like you scan over a button element, it'll highlight that button element. Would there be a quick and dirty way of maybe running over different elements, maybe in the back end, seeing those like highlighted on the app, and then basically identifying like the regions? Or I guess maybe that's not necessarily the problem. I'm thinking of like how we can like more directly identify the specific buttons, but I guess we already know about the buttons locations. I'm sorry, so I'm kind of thinking out loud a little bit. I'm not sure what my question is.
No worries. I
Yeah.
do have the answers as well. But I'm trying to think of how to make this better as well. So one way is to interface the thing in the image domain. The other way is to interface the knowledge. You can also integrate the knowledge in text domain. So what this means is that we, instead of asking the GPT to instead of asking GPT to do the actions in the image itself, ask GPT to summarize, to state intent from image, okay, in text form, okay, then map the text form to UI elements in XML space. So maybe this would work better. Like instead of saying that, hey, go to the top button or go to the left button, we ask GPT, say, go to the search bar, type in stuff in the search bar. Then after we go to the XML and see where's the search bar. Because I believe the XML elements might have some description, so you might be able to map it in the text space. Yeah. So Joni, you asked where is the XML positions, right? I believe it's in one of the GitHub repo. They actually have an XML parser. Right, you might be able to see it in the scripts folder. Yeah, you just look over there because I also found the XML there. Yeah, later if we have time, I'll show you where it is. Okay, but let's move on. Okay, because I think we are running behind time a little. But it's good discussion. Okay, I think this integration of image and text is still an unsolved problem. And honestly, the vision modules are not exactly how we do vision as well. So this is something that is a bottleneck to a lot of integrations. We think that GPT-4V knows exactly where the positions are, right? It may not. So there's many sources of failure there. But if we can integrate GPT-4V with more precise navigation abilities, I think it will solve a lot of this kind of things. Oh, so now let's move on to the domain-specific knowledge, domain-specific language. So rather than doing XY cursor space manipulation, as based on the discussion earlier, you would have realized that GPT-4V doesn't give XY coordinates very well. Neither do we actually, and neither do humans. So it might be better to just limit the action space to only UI elements rather than the XY cursor space. So here we have tap on the button, long press, which is to hold there because some buttons you need to hold longer to activate it. Swipe it in a direction with a certain distance. Okay, text is to input the text. Okay, over here I was thinking that, you might also have UID, text. I mean, it might make it more efficient, right? Rather than splitting into two steps. Not sure why the authors did this, because you need to type text in a UID anyway. All right. So back is to go back to the previous screen. It's like the Android back button. Exit is to say that we are done with the process, or we have reached the maximum steps. So this is how the domain-specific language is encoded in the, like these are the descriptions in the paper. So you can see that it takes in like basically the variable name and the integer and so on. This is also in the prompt. And they give an example like tab 5 would tap on the element labeled 5. They can read all this in the paper. I won't be going through the precise details. Okay, now we go on to exploration phase. All right, how do we do the exploration to generate the documentation? So let's see how they did it. Essentially, what we do is we take the two images, okay, and we compare the before and after, and we give the action, and we ask GPT to say, based on the before and after image and this action, what does this element do? Like here, tapping this UI element, adjust the color settings. Okay, but before we ask it to analyze the before and after, we kind of need to give an action to take. So where does this action come from? So this action comes from goal-oriented self-exploration or human demonstration. So let's go into that. So goal-directed self-exploration is actually the same way as how the agent would do the deployment. All right, you give it the task, you give it the current image, give it the list of functions, give it the past history of the actions, and then ask it to choose the next action. So the self-explore is essentially the same thing as your deployment agent. Guided, what is guided? Guided means that your human can take a series of actions and the AI can learn from that set of actions based on the, basically the human actions will lead to different states or different screenshots, and then the AI can then learn from that. So I think this is quite cool. I like this method a lot, learning from actions, the before and after, and learning from actions to figure out what exactly each UI element does. Very good, because in traditional reinforcement learning, you just learn from like state values or state action values. This is values are slow, okay, to learn. Okay, goal-directed learning is faster. So I've been advocating for this in my own research as well. And this paper, using some form of goal-directed learning, is learning really, really well. If you use RL to solve any of these problems, your success rate is close to 0. All right, so this is the new era. All right, this is the new era. I mean, the abstract, I posted that Andrej Karpathy tried to do something similar with reinforcement learning. It didn't go too far. So RL is not able to do this kind of problems. Okay, we need goal-directed learning. And that is essentially where my research is heading as well. So I really like how this paper does it. It's goal-directed learning. Okay, how do we learn from our actions? So from our actions, okay, we have the given task, the action, the before and the after image. How do we know whether the action, how do we know if the action is good? Okay, the key thing is, one way of doing this is to have supervised learning, where a human expert will give the guidance as to whether it's good. Okay, this is slow, okay, because it's very expensive to get labels. Okay, the other method that is typically used to do is reinforcement learning. Reinforcement learning, where the environment, task success, would guide the actions. Okay, but this is hard to learn because some tasks require too many actions before rewards are earned. So what can we do? Okay, these are like other methods that can be done for learning actions. So the method that they use for learning actions, I like it a lot actually. Yeah. So basically they ask GPT. So now, okay, this is the now alternative. LLMs can be their own learners. Okay, we ask LLM to evaluate whether the action is good. So in this case, we ask the LLM to evaluate whether the action is good given the task, the action, the before and after image. And the LLM will then say that, okay, back, the action is not good. Please go back. The previous step was better. All right. Ineffective, nothing changed on the screen. Okay, so if let's say you have a back or ineffective here, all right, next time around you will skip those actions. So this helps to truncate, all right, the action steps of so that you will avoid taking actions that lead to nowhere. All right, but of course there's some issues with that as well. Sometimes you might classify wrongly. So essentially this is like a classification step. Okay, it helps to truncate the tree of possible actions, and I like it a lot. Although there might be some issues when you classify wrongly, but in general it prunes the action space well enough. All right, continue means that the action is good. It has changed something on the screen. Okay, but this thing may or may not be useful. Okay, but it has changed something on the screen, and this is basically changing something that does not lead to an incorrect path. So yeah, we can still continue to explore those kind of actions because, you know, although it's not useful yet, it might be useful later on. Okay, as long as it doesn't lead to the wrong path. It like back means the action is obviously wrong. Okay, maybe you want to do Google Maps, you exit Google Maps. That is obviously the wrong step because you still need to be on Google Maps for it. Success, it means that the action has changed something and it helps to fulfill part of the task. So this, we will continue exploring these actions as well. So this is a very good way to like curate your action space using LLMs as their own learners. All right, and you don't have to rely on the task success. You can just say that, hey, this is my task. This is what I have so far. Is it good? And we don't just say, is it good in a free form? We give it categories to do the decision. So the category could be like continue, success, back, ineffective. I like this method a lot. So this I give it a star, right? Because this helps to truncate your action space, helps to do some form of pruning. And, you know, this helps a lot with exploration. Okay, so this is the prompt template. I just included it here so that you can see how they did it. So I'll give you screenshots, okay, of this action. So you already know the action. With this UI element, the action is described as this. So it could be like tab 5. For example, the action could be tab 5. And then the action was attempt to do the larger task, maybe like to do Google Maps over here. And then you should analyze whether the action is in accordance with the description of your task. Okay, and then your output should be determined based on this back, ineffective, continue, or success. All right, questions so far for this? I think this is an important slide to stop on. Okay, so yeah, I'll proceed. Okay, this is great, by the way. Next, memory or documentation. Okay, so a little blur here, but this is the documentation I got from their demo. So for example, they want to find where Bill Gates is. All right, so the numeric tag 1 says that, oh, this element is clickable. It activates the text input field, enabling the user to type in their search query. And you can say tag 24 is clickable, search icon, okay, which opens the search interface. So you can see that based on the before and after screenshots of this particular demo, like the Bill Gates one, okay, you basically know this numeric UI element 1 can activate the search query, and UI element 24 can activate a search interface. So these are useful information. Next time when you go back to the same screen, you know, okay, that, okay, this tag 1 and tag 24, you know exactly that this will do this kind of outcome. So I think this is useful. And there's something that I like even more. Okay, document learning. Okay, and this document learning is basically like how you generate this documentation. Okay, you basically prompt it with the task, the action, the before and the after image, and the previous documentation. Okay, this one I give it a star, okay, because I like this so much. Okay, you use the previous idea of what happens in the world or your previous knowledge of the world as your context to learn new knowledge. So if let's say something changes, you can update your knowledge base accordingly. So the next slide will talk more about this. But right now we talk about how the documentation is generated. So this is also very important here. They prompt to give generic documentation instead of focusing on specifics like person or the UID number. Okay, so you see, never include the UI element in description, never include the person. So that, you know, if you are searching for Bill Gates now, okay, you don't want to say that this UID helps me search for Bill Gates. No, we don't want to do that. We want to say this UID helps me to search. Because next time we want to search for Elon Musk, you want to search for Andrej Karpathy, you can use the same knowledge you have learned. Okay? And this is quite useful. So this generic documentation is very, very useful so that you can reuse the same knowledge in other situations. So this is the template for the prompt. I will give you the screenshot of a mobile app before and after tapping the UI element with this UI number. Okay, it's basically the task is this task description. Okay, your task is to describe the functionality of the UI element in 1 or 2 sentences. Okay, and it should focus on the general function. So I think this is a great prompt. Okay, great prompt not in the sense of like the length because it's still very long. Great prompt in the sense of what it's asking it to do. It gives a generic documentation which can be reused later on. And not just that, this helps us to learn when the environment changes as well. So let's say if the UI button now doesn't do what it's doing in the past, okay, this is the prompt for the refine. Okay, if there's already a documentation, okay, they give it the documentation first. This is what is generated from previous demos. Your generated description should be based on this description and optimize it. Yeah, I mean, stuff like optimize is not a good way to prompt it, okay, because, you know, LLMs don't really optimize, right? So notice that it is possible that your understanding of the function of the UI element derived from the given screenshot conflicts with the previous doc. In this case, your description could combine both, right? So I quite like this part because this means that as your UI element might come out with different functionalities, you know, it kind of combine all kinds of users. And so next time when the documentation comes out to select this UI, you know roughly what this UI can do. Okay, it's like how we can shift our memories over time to suit the new context. Okay, but one thing that's lacking here, okay, what is lacking is context dependent. So right now the memory is like same UID, always that same functions. But sometimes these functions change based on context or based on like the current screen. And that is not really captured. Okay, but one good thing about AppAgent is that for most cases, the UID that we need, the function that we need the UID to do, typically won't change. Like Google Maps, the search bar will always be a search bar, right? The book a restaurant will always be book a restaurant. So one good thing for AppAgent is that your action space will not change that drastically. For embodied agents, this cannot be said the same way, all right? Your embodied agents, your functions will typically change based on your context. Okay, so if you want to use this for embodied agents, you will either need to create a function space whereby the context doesn't really matter for your function, okay, or you need to do some form of context-dependent memory, which is also what I'm trying to do for my research, a way to embed some context into extracting out previous memories or previous experiences so that you can use that to condition your next action. Okay, but overall, this way of refining the documentation, which relies on the earlier documentation and change it iteratively, like combine it, I think this is a very powerful concept because this enables the agent to learn like the various kinds of interactions from the UI. And the reason why it can work is that UI elements don't have much functions, don't have too many functions. Okay, the moment it has a lot of different functions, we kind of need a different architecture to do this already. Okay, I'll pause here for some questions, if any. Do you have anything you want to ask about for this?
So I'm looking at this, and one of the reasons why we have a UI is because we're not really good at typing commands, right? So now since GPT-4 can learn commands much more accurate than from UI, I mean, do you see like eventually we don't need a UI, we can just say it and translate into text and translate into command directly.
Okay, you mean do the agent in the text space instead of the image space?
Right.
Of course, you can do that. I think that actually might work better than AppAgent itself right now, because GPT-4V does have problems interpreting the image.
Right.
But as I said earlier, if you just do it purely in the text space, it might be a bit too verbose, because you need to describe a lot of things from image back into text. And also some things are harder to say in text. Like for example, if I want to ask you to like find a place on Google Maps, I normally can say, oh, it's at the top right of the screen. If you want to do this into text, I mean, you need to maybe interpret this into XY coordinates. Like I think it might be a little more verbose than just image itself. But based on what I see in terms of GPT capabilities, I think it will work better in the text domain, because our image processing, as what I was discussing with Zeri earlier, is still using vision transformers and it's not very good yet. Yeah, so the vision part is, I mean, if you look at my future of AI videos, I predict that the vision part is the one that will take the longest to solve. Okay, so maybe in the next 5 years, then we can solve it. So that is still the bottleneck for interpretation right now. Text-based understanding is quite good for large language models. So I would bet that if we convert all of AppAgent stuff into text, it will work better.
Yep.
So I agree with your point of view.
Yeah. I mean, unless we can GPT-4 can interpret USD format, because USD format is a format for like 3D, and that can help us to get a lot of contextual information, and that's helpful, right? So if you walk in a park, and GPT-4 can can interpret, oh, okay, half-mile from you on the left there's a lake, and a picture is much more concise and you have all the relationship versus in text. But right now, I don't think GPT-4 can work with USD format that can actually interpret all the elements within a picture.
Yeah, so that's a key bottleneck right now. That's why it's so hard to navigate UI elements. It can't even locate precisely where the UI positions are. Yeah. Just now you said USB format. I didn't quite get that. What
USD. So USD format is a format for 3D graphics, and it's made by Plexer, so that all the objects in the
USD, is it?
3D environment.
Is this
USD? Yes, a universal scene description.
Oh, okay, I heard of it. Yeah.
So it has all the objects in a 3D environment, and it's organized hierarchically, right? And that's the key, and that's what NVIDIA is trying to standardize as their default language to compose a 3D picture. 3D scene, sorry, yeah.
Yeah, so I agree with you. I think it's still a while before we get the vision part done properly. But as of now, based on what AppAgent is doing, basically interfacing it with some precise positions in the XML, I think this is a good middle ground right now for current technology. Yeah. And I just want to recap again. This documentation part is huge, by the way. This documentation is huge. This documentation step is the reason why it's working so well. So they got the part of memory reflecting what the UI does based on the before and after images. This is what I call action-led learning. It's also in Thousand Brains theory. Jeff Hawkins also mentioned that learning from actions is the way that the brain learns for a lot of things. Okay, other than stuff like music or text, because there's no action physically. But for stuff that requires you to interact with the world, you learn from your actions. Okay, and this essentially is how we learn from actions and how we update our memory with our new experiences. So they have done some stuff like this in AppAgent, and I think this is quite useful for embodied agents as well. Okay, now we go to deployment phase. How exactly is this done? So deployment phase essentially is like this. You have the screenshot. You have your documentation about what each element does, if you have that documentation. You have your list of functions, again, the DSL functions, quite simple, only 5 or 6 functions. And you have your action history of what has been done before. Then we choose the next function using the observe, think, act, react framework. And then we summarize our action to give like a summarized 1 or 2 liner about what has been done so far. So this helps to give the context for the next state. So we keep doing this iteratively, 1 state at a time. Okay, choose the action here, then choose the action here, and so on until we reach the end goal. So this is the deployment phase. So as I mentioned earlier, this is what we get, the task, the before image, documentation, function list, past action history, which is from the summary that we get from the output here, from the previous step. Okay, and output is the function. So each function contains input parameters, what are the types, okay, how to use it, and some examples. So this, I think, is the key, okay, to how to use the functions. And, you know, I'm also doing my own agentic framework. I'll be using this 4 kind of, 4 kinds of categories as well in my own agentic framework. It's going to be implemented on strict JSON soon, okay, which is my own Python package to process JSON. So I think what they did for their prompt here is not too bad. It's just too long-winded. All right, it looks, I mean, I think this can be summarized into like half the length. Okay, so you can see that this is what they do. You have agent trained to perform some basic tasks. You'll be given a smartphone screenshot, interactive UI elements labeled with numeric text. Okay, and tag will be located in the center of each element. You can call the following functions: tap, text, long press, and so on. Then you can see this is the description of your function. Like the tap is to tap an UI element. Okay, and what's an element? It's a numeric tag assigned to UI element. And the use case will be tap 5, which shows the element labeled with number 5. I mean, what they could have done is like that. They could have done like that: tap element in, tap element on screen. They could just define it like that. Okay, I'm just showing you how this could be optimized. So, example, tap 5. Tap 5, taps element 5. Yeah, so you can see that essentially these 3 sentences, you could just give it as this very, very small succinct text. All right, and it would do almost the same thing. So I would say that whoever did the prompt engineering for Tencent, all right, you are too long-winded. All right, so I think I can do better. So when the strict JSON framework comes out, it will be more concise like that. So why I don't like long-winded prompts? Because context length matters. Okay, the longer your context length, the worse your performance for the LLM. So it's important to make it concise. Right? But the idea of this deployment agent is like, given the screenshot, given the prompt, given the past action history, given the function list, and so on, come up with the next function. So essentially, this is what the prompt does. And this is like the second part of the prompt, which is like swipe. Oh my gosh, look at this. Look at this. I can summarize this in 1 sentence or 2 sentences. Yeah. And then you see, you need to complete task description. Your past actions are to be summarized. This is the last action, which is basically given by the GPT output in the previous round. So you can see that you should go observation, thought, action, and then you summarize your past actions in 1 or 2 sentences. Okay. So you can see that the action here is what we would. This is basically the next function to call. And then this summary here is the action history for context in Nixon. No, it's quite a nice way of generating it. So they call it the observation, thought, action, and summary framework. Essentially, it's the React framework plus the action histories. And I would like to say that over here, they could have done something differently. All right, right now they ask GPT-4V to output in this format like that. Okay, and then later they use regex to, like, based on the observation, they try to come up, they can't extract out all this over here. Okay, so this is a bit of a selling of strict JSON, but you can do it with strict JSON as well. So you can just like do strict function. Basically, you could do it like that. You can do the user prompt is whatever prompt that that they have. Okay, the system prompt is whatever prompt that they have. Okay, the user prompt will be basically like the image and text tokens. And then what you can do is you can then do like the output format will be like that. So you could say like output format. So the output format is actually a kind of JSON thing. You can say that you want an observation. Describe what you observe in image. Then you can put like thoughts, actions, and so on. And then summary. And then later on, when you want to get this, okay, it's a bit hard to see it here, but if you want to get the various views, you can just use a dictionary to say rest observation, then you can get what you want. So they didn't use something like strict JSON because it wasn't really there yet when they did it. But I would say that if they use this, they would save a lot of hassle in extracting all these views like observation, thought, action, summary, like what they did in the code. Okay, so I do think that there's a lot of things that could be improved in their prompts and stuff. But the general idea of how the agent learns, how the agent is deployed, like merging the XML and the input grid and the image is quite a genius idea. So I'll give it to the authors. They did a really good job for this idea implementation. All right, this is the critique that I mentioned earlier, like prompts are too verbose, output format too free form. Okay, maybe before I go to the results, any questions about this deployment phase, but maybe just 1 minute before I go to the results. Are you all clear how this works? Yeah. Maybe if you all have any questions, you can ask now. If not, I'll carry on. Okay, let's move on then. Let's go to results. Okay, the results, as you can see, okay, let's not do the average steps and the rewards here because okay, this reward is basically how close the screen is to the end goal, and average step is how many steps does it take to solve the environment. Okay, I think this is not that important. The main thing is whether it can solve it within 10 steps. Okay, so you can see that DSL is very, very concise. For all the tasks that they have, it can all be solved within 10 steps. All right. You can see that having this domain-specific language is very important because if you do action space raw, which is XY coordinates, okay, the success rate is like 2%. And this is GPT-4V. If you use reinforcement learning, I think the success rate will be close to 0. Okay. So this is still an improvement. The 2% is still an improvement over reinforcement learning. But you realize that if we use the DSL, if we use the action space of text and so on, you can see a huge jump, 2.2 to 48.9%. That's a huge jump, which shows that if we do the constrained action space using functions, it is way better. And that's not all. If we use the documentation, which is the past memory for learning, to not repeat the errors and focus on the more correct functions, because if you label an action as back or as ineffective, right? Sorry, back or ineffective, you won't repeat those actions again in the exploration phase. So this and then you will generate documentation to say that what each UI element does. So using the auto exploration, success rate is 73.3%. Wow, that's not bad. Watching human demos is 84%, even better. And if you manually craft your instructions for your documentation, like you give expert knowledge, it can easily go to 95 or 96%. Okay, so it means that the documentation step actually captures quite a lot of things already just from GPT-based evaluation. Okay, so like given the before and after images, okay, these two here are GPT-based evaluation because let me use a different color. The auto exploration and watching demos are GPT-based documentation. And it's already doing quite well, like 80%, which means that using LLMs as a way to learn by itself is viable. It may not be the best as human experts, but it leads to quite a performance baseline. So overall, I think AppAgent shows us the possibilities of using documentation and a way of doing action-based learning of before and after to learn something nice, right? And I think the domain-specific language of constraining the action space to UI elements is a genius move. The way they integrate the input space to combine the image and the precise XML position is also a very nice move. So overall, this is a very nice paper. Any questions on this? Okay, so now I've exceeded time a little, but I like to spend about 5 to 10 minutes on the questions to ponder, if you are okay with that. So this is where we can do some discussion. So the first question is, goal-oriented self-exploration is good, okay, but it fails to get the answer all of the time. Okay, because it's dependent on the inbuilt knowledge of GPT. So if GPT doesn't know that you need to go to the search bar, you need to type in the text. No, it may not be able to get the right steps to the goal. Okay, so you might need human demonstrations to boost the knowledge. So how else can we do this? Okay, if we don't do goal-directed exploration, okay, how can we get the right knowledge without human demonstrations? Okay, so some suggestions is maybe you can include some form of random exploration sometimes. Okay, if you explore enough, maybe you will get the answer, even though your GPT goal-oriented is not used all the time. So maybe you may not want to do this. So I mean, if you think of humans, right, we do have like explore, exploit as well, right? So like you may not do best action all the time, so that you give some chance for you to explore something else. Another way to do this is maybe you have different agents primed with different kind of biases. Like maybe one agent likes to tap buttons more, okay? Like one agent prefers buttons, one agent prefers sliders and so on. So you can explore different parts of the search space. And then you combine your knowledge together. So I think this is something that can be looked into as well.
That's really interesting because maybe we can make it transferable, right? So if say for example you write the training instruction, and then I can capture the summary, and then I can import it to my agent and see how it works, and then I experiment with it and then transfer the result back to you and reconcile. That would be beautiful.
Yeah, so I believe that's that's probably a future improvement. And I think this multi-agent exploration is something that is useful, very useful. So we can look into exploring that when the GPT cost becomes cheaper. So actually, I have quite a lot of ideas on this. I'll implement some of this in my framework as well. So stay tuned for this. Any other thoughts on this? I think this is a good time to think about this because, you know, not all the time we have human demonstrations. So it will be useful if the LM can come out with the right action space on its own. All right. Next question then. Next question is about using XML. Using XML to obtain all the UI elements may not get everything that's needed. Okay, because like sometimes the UI elements like scrolling on the map, you know, it's hard to define. And to go up, I scroll this direction. Yeah, I mean there's granted there's a swipe button, but you know what if the entire Google Maps is not a UI element? I mean theoretically it should be, but it's not that obvious how we want to do all this for very free flow interfaces. Can there be another system to output the UI element positions? Okay, for example, like segment anything. Could segment anything help? I honestly don't think it's that great because like it may not get the right UI as well. Or could there be a separate action space for scrolling? Like for example, if you have a map, like go to like position, go to destination. Like maybe you could have a go to initial pause, destination pause. So you could have another kind of BSL where you can like do what the human does, like slowly go towards the end goal. Yeah, maybe that could be a way to do more complex tasks, right? To add more functionalities in the agent. So that can be explored in future work, I believe. Right? So the next is, could the overlay of the UID block some critical information of the app? Okay. So my answer is yes. Yeah, so this is a limitation. So maybe have the UID values and positions as a separate image. Okay, then the last question is basically how else to incorporate these multiple abstraction spaces to an agent. So like we have the image domain and we have the text domain. Maybe you could do processing in image, which is like what the app agent does by functions, does by UID. Or we could also do processing in text. Basically like come up with list of generic steps. Yeah, so there are different ways to do the processing by functions, processing in free flow text. Yeah, so there are ways to process the information in different ways. So very broad-based actions, very specific actions. These are different abstraction spaces. In the input side, okay, we also have different ways to abstract our inputs, like in the text domain, the image domain, and so on. I think this is an open question because how we, as I mentioned earlier, okay, the input and outputs abstraction spaces define the capabilities of an agent. So this is probably something that needs to be looked at in future agentic papers as well. How can we do these multiple abstraction spaces? Because I believe that to solve generic problems, you can't solve it in just one abstraction space. You need, like, for example, in this case, you cannot just have the image alone because you miss out on maybe very precise UI positions. You need the image and some text. Even better if your text can have the description of the functions as well in the XML. So different input views help us with understanding the problem in different ways, and different output views, which is basically like giving free flow text and giving functions, will help us to give better responses because we can look at things in different angles. If you look at the React framework, let me just quickly zoom back to the React framework. If you look at the React framework here, okay, I wanted to find the one with the this one. If you look at the React framework here, you will see that they already have combined multiple abstraction spaces. Okay, so like for example, this thought here, I need to tap on this search bar. This is more of a free flow text-based abstraction space. And then when you go to the action, this will be function-based abstraction space. So this is why I think React works so well. It flows through from the more broad action spaces into a very specific action space. And this way of processing the output via different abstraction spaces like this, okay, or rather people call it chain of thought, okay, this is very useful. So this can be done also at the input level. You can have different inputs come out with different views, and then you combine them together. And then you can process them in the output like that over different abstraction spaces as well. So at least this is what I'm thinking. Philip, you asked me what do I mean by free flow, right? What I mean by free flow means that there's no constraints. Like when I asked it to generate the thought over here, I did not give it like any kind of like functions to map into. You can just give a free flow response. So these are I always believe in this thing called the general to specific generation. So you can like guide your specific generation based on what you have decided in the general. So in some sense, this is like a hierarchical way of processing. Helps to focus efforts. And the React framework does just that. That's probably why the React framework does it so well. Okay, it need not be just React like that. It's the idea of going from a general space to a specific space. That's very useful. And in the image domain, the idea of combining multiple abstraction spaces together. So you have an image here. You have like a text here. Maybe the text is like the UID positions. All right. Combining all this as an input space is very useful as well because it can help you get different views. All right. And I do think once we have mastered how to get various abstraction spaces well and use all this information together, like right now they process this in function space, okay, but there are different ways to process this. Right now it's all processed using the image as the key because we say that we want to navigate to UI element everything is based on the image here. Okay, but what if we convert this image down? So this is another thought. What if we convert this image? Describe the image. And then your text, the UID positions, will go inside this describing space. Process in XML space. Now we could also do that. Yeah, instead of processing everything in the image space, like tap the button and so on, we could do everything in the XML space. And maybe that's what's already done because they provide the XML as well. So there are different ways to process stuff, and different ways of processing leads to different biases, and it might help in solving different kinds of problems. So okay, maybe instead of process in function space at the top, I change this to process in image space. Okay, so I think this is probably a good point to end. You have any things that you want to discuss before we call it a day? All right, if not, yeah, thanks for coming. Yeah, I think this AppAgent is really quite cool, and yeah, do try it out. I haven't really had the time to play around with this on the Android emulator, but looking at the code, I think it looks quite decent. So do try it out, and yeah, see you all again soon. Okay, bye.
Bye. Thank you.